We've studied a lot of different ways to create power, and there are important quantities to compare those. So there are questions. Why do power stations use coal instead of wood? How can we quantify the difference? Why do cities build nuclear power if it's so dangerous, those radioactive byproducts? Why do countries fight over oil? So to answer those questions, we need some objective standards to evaluate and compare fuels. And here are the 3 that you get as part of the, maybe 4, as part of the IB physics course. So the first, of course, we've seen already, power. It's the rate at which work is done. Because it's a rate, we have time in the denominator. Or it's the rate at which energy is transformed. Specific energy. Where is the last place you saw the word specific? It was specific heat, which was Q over m delta T. Specific means divided by mass, or per unit mass. Specific energy, then, is going to be the energy released per unit mass when a fuel is consumed or burned or utilized. Because it's fuel we're talking about, this is the input energy. Up here, this could be the input or the output, depending on whether you're looking at electricity or the fuel. Energy density is the energy released by the fuel. So that's input energy that the fuel is providing. And then you take that fuel energy, you convert it into electricity, and there's less electricity at the end than you started with input fuel energy. So you take that input energy from the fuel and you divide by the volume. So per unit volume. Efficiency, this is really the symbol for thermal efficiency. It's the useful work that you get out divided by the input work. Or you could do the same with power. And the important thing to remember is that the output is always the electrical energy or the electricity. And the input is always what the fuel provides or releases or generates or carries. Right? We've talked about primary fuels already in other contexts. Those are the natural resources that can be burned or reacted or just acquired without any prior conversion or transformation. So that includes things like sunlight, wind, biomass. We haven't talked about geothermal heat, but you can extract heat from the earth itself. Tides, waves, rain, all of those sorts of things. You know, rain, you don't have to extract it. You don't have to transform the rain to get some energy from it. Non-renewable sources that are primary would include coal, oil, petroleum, natural gas, uranium, that's for nuclear energy. And the way we distinguish between these categories, renewable and non-renewable, we compare the consumption rate with the natural replenishing rate. So it's I'm not going to write those definitions out, actually. I'm going to have you do that as an exercise. Do a comparison for renewable. The definition would be fuels that are, what would you say, consumed more quickly, less quickly, that are replenished more quickly. You could phrase this a couple ways. Take a moment to put this down into words. Define renewable and non-renewable energy sources. And it can start the same way. Fuels that are something more quickly than something. Now, when you look at these equations, you're going to start to see ways that they can connect. Maybe we'll give you the energy and the time, and then you have to calculate power, the input power perhaps, and then you have to plug that in right here. we give you efficiency, and ultimately you find the electrical energy or power produced. Maybe you're going to see other problems where we give you the specific energy and the mass, and you have to calculate the input energy, plug that in right here in place of, that would be input, plug that in right here, calculate the work output from a given value of efficiency. And so you can imagine different ways that these can be. Don't forget the equation of density. That's a good one. Not energy density, but just regular mass density. How dense is the mass versus how dense is the energy? And maybe it's worth writing down efficiency. You can write this in terms of energy. The energy that you produce divided by the energy that you're putting in, that the fuel puts in. This is the electrical, and this is the fuel, always, for all of those equations. And so now you're going to get to see some problems that combine these in different ways.